Okay, I think we can get started. It's my great pleasure to introduce David Pynadath, a research scientist at ICT. I was lucky enough when I arrived at USC, when I first arrived in the US, David was in the office next to me, and he told me anything I know about POMDP, everything I know about American sports. I think he has a very prestigious record as the only person to have won a Best Paper award in a major conference and a fantasy football and fantasy baseball league all in the same season. So, very impressive. It has very, very elegant theory, but I think the most impressive part about this is he really makes it work, and I think this is going to be a great talk. So thank you.
Thanks, Paul. So I just want to start out by parsing the title of this talk a little bit to give some context about what I'm going to be talking about. And when I talk, basically the problem I'm addressing here is modeling social reasoning. The method is sort of the second part of that title, and that's less important here. But in terms of reasoning, I'm talking about decision making, and this is something that translates across people, software agent systems, robotic systems. Basically, anytime you have some entity choosing between alternate plans, behaviors, actions, etc., and they're doing it not randomly, but actually towards some end. They're trying to achieve some goal, make themselves happy, achieve some sort of utility, some sort of optimization. And it's social in the sense that there's a social setting, in that it's not just that they're trying to achieve some task in a domain, they're also they're worried about the impact of their actions on other agents, other people, other robots. And they're also worried about the future actions of those other agents and other people and other robots. So they're going to take an action, it's going to have some domain effect, but there's going to be a response as well. And they may also be worried about the impact that their actions are going to have, not just in the domain, but also on the beliefs that other people are going to have, which may affect their performance in the task as well. So it's not a problem of addressing the domain in isolation, but also worried about how we're going to actually affect other people and other agents and other robots. And we're modeling this in that we're building a computational model of how to do social reasoning. And this could be a descriptive model in that we're looking at perhaps people trying to capture a computational model of how do people make social reasoning, how do people make social decisions. But we can also turn this model into a prescriptive model in that it says, how should people make these decisions? How should agents make decisions when interacting with people? How should robots make decisions when interacting in a domain? And we can sort of combine these two into sort of also what I'm going to call a generative model, where we're not necessarily making a prescriptive model, but we're also just trying to create an agent that can generate certain behaviors, perhaps for like an entertainment story. We want to create a video game, and we want to generate behaviors, and so, but that are sensitive to social reasoning as well. Okay, so we're talking about computational models for multiple purposes here. And just sort of to give an illustrative example, I'm going to focus on a decision-making context, which I hope is at least intuitive enough, which is of a schoolyard bully who may have a certain reason. He's been studied a lot in psychology, and if you want to sort of like open his head and think about why is he actually picking on his victim the way he is. And one possible reason that's sort of you can find in the literature is that he doesn't like this kid, he wants the kid to suffer. Okay, that's one type of childhood bully you see. There's another type of childhood bullying which is done, well, it's really more strategic in a sense, in that he does it to make himself appear more popular and stronger to the other kids in the setting here. And one of the challenges for child psychology is that, well, there are these two different types of bullies. Can we decide if we're actually faced with a certain bully in a certain classroom that we want to deal with? We need to actually figure out what type of bully that is. And so this provides sort of a descriptive challenge for computational models, in that we want to build sort of a social simulation where we want to be able to study human behavior and create a computational model of it. But this is really hard to do, in general, because, well, we can't always control the conditions of an experiment. We can't really isolate bullying. We can't put a bully and a victim in the same room and watch them go at it. We can't examine all the outcomes that come out. So, a bully picks on his victim. How do the other kids change their opinion of the bully? We kind of know that they might think he's a cooler kid now, but we don't really know. We can't really survey them and find out very accurately. And we obviously can't repeat the experiments endlessly. We can't just, again, the bully picks on the victim, okay, great, break, go to opposite corners, start again. And so this is really why a lot of social psychologists are really attracted to computational models, because we can run those many over and over again. So if we have a computational model that underlines both possible types of bullies, we can vary the parameters of the model to say, like, oh, here's a computational model of a bully that wants the kid to suffer. Here's a computational model of a bully that's looking to gain approval of his peers. And then we can examine the consequences of the simulated entities, and then we can see which one best explains the behavior that we see in the real world. Okay? And so this sort of gives a methodology for how you can take a descriptive model of a theory and use it to get insights from the real world. And there's another issue here, before I get getting ahead of myself here. So it's not just the bully and the kids. We hope that there's some supervision here. And there's a third factor that the bully is considering. What is the teacher's response going to be? So is the teacher going to punish him? And if you think about this from the perspective of not modeling a bully, but actually looking at what the teacher is thinking about, if we build a computational model of this bully, we can imagine that the teacher has different courses of action. So for example, we could actually build a model of the class and study the different punishment policies and their effect. So this is sort of we can look at this as possible prescriptive model use of computational models. So we can build a computational model of the classroom, implement hypothetically a particular punishment policy, and see whether the bullying persists or not. And then we can look at the simulated outcomes and say, oh, under this punishment policy, the bullying stopped. Under this other punishment policy, the bullying did not stop. And then the teacher could have some confidence in implementing in a punishment strategy without having to sort of resort to a more trial and error approach. And you can imagine this is obviously translate to a wide variety of domains, studying the possible outcomes of health interventions, emergency response, et cetera. Basically, the idea here is that we try out policies in a simulated environment, find out which ones work best, and that becomes a prescription for our real-world policy as well. Now, so if you imagine like what was going to happen here, so if we have a bully of a certain type, we have a bully that doesn't want to get punished, then the teacher could say, well, I should punish the bully. Okay, so this would be one scenario, possible story setting where the bully is looking not to get punished, and punishing the bully is a good thing to do. But you can imagine a different classroom where the bully doesn't really care about not being sadistic, but actually wants peer approval. And maybe one way of removing that possibility of peer approval is for the teacher to punish the whole class. And these are two different scenarios, and one possibility is that you could actually get real-world data to get that kind of outcome. But another possibility is that you can offer this as a possibility for the bully himself to play out a scenario and see the consequences of the actions, and teach the bully himself about what's going to happen if he does the bullying. So rather than have the bully learn by being punished or not, actually provide the scenario and have the bully play the game and see the consequences of his actions. So he can practice behavior, say, oh, I don't like this kid, I'm going to pick on him in the game, observe the real-world consequences without there actually being bullying in the real world. So you can imagine this becoming like a video game, serious game about bullying, where they can see the consequences to themselves, and they can also see things that they couldn't see in the real world. So you can actually see the consequences to the other people. So if the bully is looking to gain the approval of other people, maybe you can have a game that teaches them that the people actually didn't like them, and maybe even receive a score. So the bully can do the picks on the kid, the teacher tells him to stop, and the kids that like him more, he can see that he'll get punished, and maybe that'll dissuade him. If you want to make a stronger message, you can actually change it. Oh, okay, that was wrong. You can actually change this behavior so that the kids actually don't like him as much. And then that you can actually, instead of actually necessarily modeling reality, you can amp up the message by changing the response of the agents to be more negative in their impact. So you can actually have the onlookers, the other classmates, like him less. Even though they might actually like him in reality, you can give the message to the bully that if you pick on him, the other kids are going to like him less. And this sort of leads to a more generative model, which is not necessarily descriptive or prescriptive, where someone is actually authoring a fictional scenario. So we're not necessarily looking at modeling reality, but actually creating a scenario that captures some sort of authorial intent. So if you imagine the types of settings you could make for bullying, well, there's a wide spectrum of stories. And here you can make a very innocent childhood story to something a lot more darker and satirical, like Lord of the Flies. And the idea here is that someone is taking the concept of bullying, but building a much more, but putting an own personal stamp on it for a variety of reasons, either to convey a certain moral, teach a very simple lesson, or have some other themes as well. And this is what I'm going to refer to as interactive narrative, where there's sort of characters that are being driven by some AI technology, and that the person takes certain steps, actions in the simulation, and goes through a story of some kind, not necessarily through linear paths, but sort of in where they can have more open-ended interaction with the characters. And if we think about what it takes to author these social simulations, well, there's sort of this tension between two different demands. We want lots of possible behaviors to be captured by the underlying multi-agent system. So from a psychological point of view, if we look at the real-world possible behaviors of humans, there's a rich space there. I mean, there's a wide variety of behavior across the spectrum of humanity. And so we need our agents to be able to capture each and every one of the 7 billion possible human behaviors that are out there if you want to have true psychological validity. From an educational standpoint, you want the students to learn, which means that you need them to be able to be free to make mistakes and then get the feedback from the system. You don't want them to be constrained to follow down the successful path because they're not going to learn really. They'll just be following that lockstep mindlessly without learning what happens if they stray off that path. And from an entertainment point of view, if you think about this as a video game, well, you want them to be, it needs to be a rich enough world that there's freedom to explore. So you don't want them to be constrained to follow a path, a linear script. That's not nearly as engaging as it might be in a more open world. Okay, so that's sort of the one end of what we want. We need to have a technology that allows us to express many possible behaviors. But on the other hand, when we want to build a specific system, we really have only one behavior we want. Okay, so from a psychological standpoint, yes, it's great to have an architecture that can model 7 billion people, but if I want to model one specific bully, then I need to be able to figure out which model corresponds to that one bully. So I don't necessarily need, I'm not caring about all 7 billion people all the time. And from an education standpoint, well, it's not enough to build a really rich environment. I also have to make sure that the lessons is learned. So I mean, it's great to allow the bully to do all sorts of things in the simulation, but at the end of the day, I want to make sure that if he does the wrong action, that he's punished for it in the simulation and gets that negative feedback. And from an entertainment point of view, it's like writing a book. You can write, it's very easy to write lots of words, but to make a good book, there's obviously some constraint there in terms of becoming entertaining, well-written, engaging. And it's just as true for a computational-based entertainment as well. We can generate lots of behaviors, but we want to make sure that there's some story, there's some sort of theme, etc. And so if you look at the approaches that people have taken to actually being able to author these rich environments, well, one aspect is to sort of program the behavior. So I put rules in parentheses, in quotation marks, because they're not necessarily rules, but the idea is that you're trying to encode the behavior of the agents in some sort of program that allows you to say, like, in this situation, so example, if the bully picks on the victim, the teacher is going to punish him, right? And so this has the good aspect of whatever the author wants the behavior to be can be directly encoded in these heuristics. So the author can directly say, if the bully picks on the victim, the teacher will punish him. If the bully picks on the victim will not retaliate, etc. Now, if the bully picks on the victim and the students laugh at him, okay, now we need to add a new rule. And if the principal gets involved, there's another rule that needs to be added. If the victim retaliates, etc. And so we can directly control the behavior by encoding these rules, but the downside is that we need to be able to anticipate situations in such a way that we can write rules that cover these situations in an intelligent way. And as the number of sort of agents increases, as the number of situations increases, we end up with a sort of combination problem where we need to be able to actually anticipate the interactions of these rules. And we sometimes need to write rules that sort of have combinations of these effects on the left-hand side, and it becomes more and more complicated and harder to actually write the correct rules in our heads and then put them into the system. So an alternative approach, rather than relying on the author to write down what the behavior should be, is to take a more planning the approach. Where the agent, rather than being told what the behavior is going to be in each situation, adopts a more deliberative strategy. So he's given a certain situation and uses some domain-independent planning algorithm to say, okay, well, this is what I'm thinking in my head. This is what I believe the world is. These are the kind of things I want to achieve in that world. And let me reason about the possible courses of action and choose the one that makes the most sense to me. Okay? Now, this has the aspect of being more robust to new situations in that whatever situation the agent finds in, it has a more first principles reasoning that it can go through to figure out, okay, whatever situation you plot me down in, I'm going to consider my possible actions, consider the outcomes, and then pick the action that may be best achieve them. So we can reuse that planning out. The idea here is that there are mental states like preferences. So if the bully doesn't like this kid when there are 20 kids in the classroom, if we add a new student to that classroom, he's still not going to like his victim. Okay? If the kid doesn't want to get punished, if we can add a new principal, he's still not going to want to get punished. Right? So those kind of mental states are sort of more invariant to situation. At least that's the hypothesis here. And similarly, we can reuse a planning algorithm. So whatever situation we can be in, it can execute that exact same planning algorithm, just plug in the new input of what the new situation is, generates a behavior, and we're still good to go. The downside is, from an authoring point of view, is that we've now sort of broken the intuitive connection between the input that's going into the model and the behavior the agent is going to take in. So we have some planning algorithm that's been introduced, and often we're talking about some black box planning algorithm that's sort of generating actions. And it's no longer clear when we enter something like, okay, the bully doesn't want to get punished. Okay, what does that mean in the situation? It's no longer as clear what it means. Like if you increase the distaste the bully has for being punished, does that mean he's more or less likely to be bullying the victim? Okay, and so we have these two sort of approaches of programming versus planning behaviors. And as you may have guessed from the title of the talk, I'm more on the planning side, and because I think these pros are very useful, and I think these cons are things that can be addressed through research. And so that's what I've been working on for the last decade or so, and it sort of resulted in a system that we call PsychSim. It's a multi-agent-based social simulation where agents represent the different beliefs of the people belief or entities, and they reason from those beliefs to generate the behavior. And that's pretty well understood, and that's relatively straightforward. I'm going to explain that first. But then the larger question is, and we'll see how much detail I can go into that, is, well, okay, now what does it take to make authoring easy? Okay, so we've broken the intuitive connection between the modeling and the behavior. How can we reestablish that connection in the minds of the author? Okay, because the agents can generate, again, lots of behaviors. We have a very rich behavioral space. We have lots of parameters we can play with and generate lots of behaviors, but we don't want lots of behaviors. The system designer does not want lots of behaviors. The system designer wants one specific behavior out. And what's really important here is this last bullet is, okay, I've been working on POMDPs for almost 20 years now, and yes, I can probably take your domain and build a POMDP model of it, but that's not really of much use to the world at large. People in general, if they have a problem, they want to be able to build their own system, use an existing AI technology. And so the question is, what does it take to take something like an AI technology like a POMDP and make it available to someone who's a social scientist or someone who's a historian, et cetera. And so that'll be the second part of my talk, is the efforts to be taken to try to make the AI technologies available to people who are not AI experts. But I'm first going to begin by talking about the social simulation architecture itself, trying to explain what the mechanism is by which we try to model the reasoning that people do. This is our first attempt. We sort of started with a board, and we started writing down all the features we need to capture to model a small 5-entity scenario. And after a while, we realized this is untenable. We can't just write down a model that tries to capture all these different features and tries to capture all the interactions among them. And basically, what the trouble was, we were looking at the final features and looking at a description of all the different entities and trying to capture them all on the board and then look at the interrelationships among them. So we decided to take a step back and say, well, what is it about social reasoning that's hard or that's important? And again, there are two things here. There's decision making. There's choices to make. There's uncertainty about the effects of those choices. We don't really know what the impact of an action is going to be on another person. And there are trade-offs among conflicting goals. So we got preferences, and we want to make more money, but we also don't want to take advantage of people to a certain degree, but we're willing to take advantage of people to a little bit of degree to make some money. How do people navigate those kind of trade-offs? And importantly, even in just that example I gave, is that there's a social context, and that there are other people who are reacting to decisions. There are other people who may respond to how we behave, and we may value their opinion. We may want to be respected in the community. And then there are second-order effects. It's not just I'm taking an action, it advances my goals in the world. It also there are consequences that the people around me respond, and then they may tell other people, and it's going to trickle on, cascade along the whole wide social network that I may not be able to anticipate. But if you look at these two platforms, decision-making and social context, and we look at, well, what does that map into from an AI perspective? Well, one way of doing that is take the decision-making and let's model that with decision theory. We have a model of beliefs. We have probabilistic model of beliefs. We have model of preferences. They're quantitative, so we can measure things like how uncertain are you about another person? How much are you willing to trade off one goal for another? And it's a long enough history that there's plenty of domain-independent algorithms we can grab off the shelf and try out. The downside of decision theory is that people, it has prescriptions of rationality that people often violate. Okay, so there's still an open question of, okay, well, we can take decision theory. It seems to capture what we want, but it's not a perfect fit for people. Similarly, we can take theory of mind, which is the model which is one approach to capturing how people reason about each other. In an AI context, we can realize that through recursive models. So it's not just that. So in psychologically speaking, we can say, I have a model of Paul and what he thinks, and I have a model of how Paul is going to behave and how he may think about me. In an agent's perspective, that's like, well, agent A has a recursive model of agent B, which is also an agent form, which may have beliefs about agent A. And we can model each other as using decision theory as well. So again, we're looking to reuse things as much as possible here. So we can take the decision-theoretic model that I'm using for my own planning, and then I can apply it to Paul to generate expectations of how he's going to behave as well. So I am applying decision-theoretic planning, and I model all other people as using decision-theoretic planning as well. And but at the same time, my model of someone's decision-theoretic planning may not necessarily line up with what they're actually doing. It's filtered through my own subjective view. There may be misperceptions, et cetera. So if you look at what a Markov decision problem is going to be, this is our representation of a decision-theoretic planning problem. And so really, if you look at the components of a Markov decision problem, these are the four key components. We have a state space. So for example, we may represent how happy is the bully, how happy is the victim. There are certain actions. These are the decisions that the person can make that we're trying to capture. The bully can pick on the victim or not pick on the victim. The teacher can punish the bully. The teacher can punish the class. And there's a transition probability that represents the effects of those actions. So if we pick on if the bully picks on the victim, then the victim's unhappiness goes down. And this may be a deterministic effect. It may be a probabilistic effect. So if you pick on the victim, maybe the victim becomes unhappier, or maybe the victim retaliates and then makes himself happier. And there's a reward function. So this captures sort of the preferences. What will make the bully happy? So clearly, if the bully is sadistic, so the bully is clearly going to want to maximize his own happiness, but he may have other goals as well. He may want to minimize the happiness of the victim, or he may want to maximize his popularity within the class. Okay, and so you can capture, and then there will be weights associated with these different reward components that sort of represent the different trade-offs among them. So let me just give a simple illustration here. So in the action space for the bully, he can pick on the victim, that's the top action choice, or he can not pick on the victim. Okay, let's just boil it down to a binary decision. Now what goes on through we're going to look at a sort of a capsule summary of a decision-making process. This is not necessarily representing what the bully is actually doing in his head. What we're trying to do is generate what would an MDP model of this spit out, and then how can we use that to sort of capture the effect of the decision-making that the bully has. But it's not necessarily isomorphic between what's going on inside the bully's head. Most bullies are not this deliberative, as we'll see. So let's look at what happens if he picks on the victim. Okay, so the transition probability is going to describe the effects of the picking on action, and basically the effect is that the victim's happiness goes down. Okay, the red arrow below the victim means the victim's happiness goes down. Okay, and if the bully has a reward that says minimize the victim's unhappiness, that means his reward is going up. So when the victim's happiness goes down, the bully's reward goes up. This is a good thing. This is an incentive for the bully to pick on the victim because he's going to make himself happier, get more reward. Okay, so the reward is really the incentives for certain actions. Now, if this were a very myopic bully that did not look too far into the future, was not really worried too much about the consequences of its actions, we could end right here, and we'd have a model of a very sadistic, short-sighted bully. Okay? But if you want to make a bully that's probably a bit more realistic, he's also going to consider, well, what is the teacher going to do? And the teacher might punish the bully, in which case the bully's happiness is going to go down, and his reward is going to go down as well. Okay? So this is the model we have. Punishing affects the happiness, and then we can sort of look at the overall value of the action. This is the course of action when the bully picks on the victim, and the overall value, V, of this action is going to be the sum of the increase in his happiness from the initial immediate response of picking on the victim to also the decrease in reward that comes when he's eventually punished. Right? So this is sort of capping this is a very simple model of bully taking an action, anticipating an effect, and then aggregating the effects over the sort of horizon of time he's looking up. Now there's sort of a missing part here. I mean, the transition probability describes the effect of action. That says, okay, if you pick on somebody, they become unhappier. If you get punished, then you become unhappier. But what's missing here is there's nothing that says, what is the teacher going to do? Okay, there's nothing in the transition probability that says a teacher is going to punish the bully. So the next step is, well, how does the bully actually anticipate what the teacher is going to do? And this is where the theory of mind, the recursive models come in. Okay, so we go into a space where the teacher has her own POMDP, or MDP in this case, and she's looking at, well, what happens if I punish the bully? And she may have an impact that's a model that says, if I punish the bully, then the bully is not going to pick on the student in the future. Okay? And if I don't punish the bully, then the bully is going to pick on the victim in the future. And if the bully picks on the victim in the future, then the victim's happiness is going to go down. And that's something that's bad for my reward. I want all my students' happiness to be going up. Okay? So the teacher is going to use her own MDP process to look at her actions. And keep in mind, this is actually not the teacher herself. I should be careful how I'm phrasing this. This is what the bully is thinking about the teacher. So maybe in the real world, the teacher may not actually punish him. But this is what we're using here is the bully's expectation of the teacher, which is actually the only thing that's relevant to the bully's decision making. Right? Okay. And so we can reuse the same MDP mechanism for the bully to generate an expectation of what the teacher is going to do. And the teacher herself, when she thinks about whether the punishing is going to work or not, is then going to use her own MDP to say, like, if I punish the bully, that's going to make the bully's happiness go down, and now in the future he'll know that if he picks on a kid, he's going to get punished, and will be less likely to do so in the future. Okay, and you can do this. You can do that recursion forever. Typically, you can bound it to 2 levels of 2, but that's sort of more of an empirical question than a theoretical question. And what's nice here is that we've got this overall expected value that it's sort of a standard MDP algorithm that can say, okay, if I've got this ability to go in and compute expectations of what the teacher is going to do using this recursive models, and at the end of the day I can compute an expected value of picking on a victim, we can reuse that computation to do more than just action selection. So one of the key things here is that, okay, I can compute the expected value of picking on a victim. I can also compute the expected value of picking on the victim to my classmates, right? So I can actually look at things like, okay, I'm going to pick on the victim. That's going to make the victim's happiness go down. That makes me happy. But you can also have a model of what the student's preferences are in reward function, and which allows you to say something like, if I pick on the victim, and the victim's happiness goes down, what does that do to the reward of the other students in my class? If they don't like the victim, the fact that the victim's happiness goes down may make them happier as well. That's going to increase their reward. And if it increases their reward, then you could say something like, well, that's a good way to model liking, for example. Let's say you want to model whether someone likes somebody. One thing you can do is, has that person, you can build sort of a general purpose model of liking by saying, people who do things that advance my reward, I like those people. So every time, and this is this exact same calculation as before, you say, okay, the bully has taken an action, picked on the victim's happiness goes down. If for somebody like the student who wants the victim's happiness to go up, that's an action that makes the teacher like the bully less. If it's somebody like a student who doesn't like the victim too, then that's an action that's going to make that student like the bully more. Okay? And what's important here is that we didn't need to add any additional modeling to capture that liking, right? The agents already have their own reward functions, and now we have, just by using the exact same mechanism again, we have a way to model how much people like each other without adding any additional components to the model. Similarly, we can do things like belief updates. So if we're not sure if this, because maybe the teacher is someone who doesn't care about bullying and is going to let stuff go, okay? So would we actually decide, how does a bully actually anticipate whether the teacher is someone who's going to punish him or not, okay? Well, the easiest thing to do, one simple Bayesian way of doing this is to do an update where you say, well, I assume that most people are going to take actions that are trying to achieve their preferences, okay? So if they take an action that is consistent with a set of preferences, that means that model is a more likely explanation than one where it's not consistent with those preferences. So for example, we have 2 possibilities here where the bully is thinking, is the teacher going to not punish me or punish me, right? if the teacher punishes him, then he can look at, okay, well, that's consistent with a teacher who doesn't like bullying. And because if she's a teacher who doesn't mind bullying, then why would she bother to punish me? So it's a very low probability that she would punish him if she doesn't care about bullying. And again, how does it figure that out? It does the exact same value calculation. It looks at, okay, I have two possible models of the teacher, one where the teacher likes bullying, doesn't like bullying, and one where she doesn't care about bullying, let's say. And for each of those models, I can say, what's the value to the teacher of punishing me? And for one of them, it's going to be higher, and for one, it's going to be lower. And the one for which the value is higher, we can say, is going to be the more likely explanation. Because again, we're going to assume that the teacher is more likely to take actions that help her reward than take actions that hurt her reward. And another piece of work that we've done is to use that exact same value calculation to model emotions through cognitive appraisal, where basically the idea here is that cognitive has several dimensions of like you model congruence. If an agent takes an action that is in line with my goals, or not in line with my goals, you take there's dimensions of novelty. How unlikely was this action? And there are other similar dimensions. And really, all the dimensions that go into cognitive appraisal are actually already calculated in the expected value calculation. So something like motivational congruence is really, again, an expected value calculation that says the agent takes an action, how much does it impact my reward or not? Okay. So you can actually decide, so again, it's reusing the exact same algorithm for expected value and trying to figure out how can we actually take that algorithm and reuse those values to capture the different phenomena that exhibit in social phenomena. And what's nice here is that, again, we don't have to add additional modeling components here. So belief update, well, that's, again, we have a model of preferences, we have a model of beliefs. We can generate behavior, we can do belief update, we can do liking, we can do cognitive appraisal, all without adding additional modeling components. So we avoid the problem where you're building an architecture by adding a new box to your architectural diagram for each of these features. We use the exact same model and add an architectural algorithm that can actually use the existing modeling components to capture those phenomena. If you have the MDP components, it allows you to have pretty complicated communications. You can say things about the state of the world. It's like, my happiness is higher than your happiness. You can say statements about your reward function. It's like, I want you to be unhappy. Statements about beliefs. The teacher doesn't care about you. Nobody thinks you're a good person. And again, these are not things that we have to add explicitly. These are just statements about aspects of the model or beliefs that are already present. So we no longer, so again, without actually explicitly adding something to the model, we have an implicit message space that can be used for rich communication among the agents. And so we've used this to sort of build the underlying architecture to sort of build a variety of phenomena. And if in the questions or after the talk, if you want to hear more about the details of any one of these, feel free to ask. But I'm going to go on to talk about the second part, which is, okay, we've built this architecture. It can capture a lot of these phenomena. It can generate lots of behaviors. But again, we're not interested in generating a system designer taking this architecture wants to use it to model a specific scenario, a specific behavior. And again, how do we get them to do that? Well, if you look at the problem, first thing we did was we built a GUI. And it said, okay, you can create a whole bunch of entities, throw them in a class hierarchy, and there you go. You can start creating these different agents. And each of these agents is going to have a bunch of state features, and they have sliders, so you can give them values. They can have different actions over here, and you can that are directed at different people. And that really doesn't solve the problem. It's nice. This is actually a scenario created for a training application. But what's interesting here is that this is a lot of sliders. Okay, and yeah, it's great that it's very easy to have. You have a graphical interface. You can throw these features in, things like location and physical security and political power and economic power. But then someone actually has to figure out what numbers should be assigned to these. Okay, because again, we want the quantitative values so that people can make fine-grained trade-offs between uncertainty and risk, et cetera. Excuse me?
Can you randomize this value?
Sorry, what?
Can you randomize this value?
Oh, sure. Yeah. But in general, this is being created by someone who's trying to capture a specific scenario, a specific behavior, and what they often are describing something that they have a target that they want. So they often have a notion of that there are two agents. One of them is richer than another one. So they don't necessarily want them to be random, but they don't know what exactly the specific values are. But they may have relationships they want to preserve. That one agent is richer than another one. The bully is stronger than the victim. So one question here is, this is an issue that comes up because again, it's great to be able to create a complex scenario with 80 different entities, and each entity has 20 different state features, but then you actually need to specify the specific values for these things. And the challenge here is, okay, so it's easy enough to create the richness, but then how do we actually get the specific behaviors out? And if, let's say numbers are hard, okay, so maybe the people, we know that they have economic power, we may know who's stronger than another person, but we may not know specific values. But if we don't know specific values, what do we, yeah, Thomas.
I kind of lost the thread there.
Sure.
Going from the previous slide to the one before that. So I was reading with the recursive MVP stuff.
Okay.
How do you go from, let's say you had perfect values on your slider somehow.
Yeah.
How do you go from that to the MVP model?
Oh, this is just it's a factored MDP. So this would be this is the state space. So these would be the dimension. These would be the different components of the vector of the state space, and these would be the continuous.
The moral authority factor into the MVP.
Someone has to build that transition probability that says moral authority. If you do something like build a hospital, then your moral authority will go up, and then you may have a reward function that's derived from what your value of moral authority.
So the recursive MVP models are all manually created ahead of time.
Yeah. So what I'm talking about here is we first built a GUI that allows someone to manually build it, and of course that's hugely labor intensive to build these things and problematic. What can we do to make it to alleviate that effort? Okay. So the question here is again. So these are manually created features and numbers. What can we do to make it easier to author them? And so one thing that we found in dealing with people who are subject matter experts, either social scientists or historians or cultural anthropologists who are experts in these areas that are being modeled, is, well, they don't necessarily know, they can't really say how much moral authority someone has, okay, that's, let alone how much physical security they have. But what they usually can say is that, well, if this certain situation were to arise, so for example, if the teacher were in the room, the bully would not pick on the victim. But if the teacher were out of the room, then the bully would probably do something. Okay, so they can hypothesize real-world behaviors. Okay, so they can again, and this gets back to the previous, the initial distinction between planning behaviors and programming behaviors. It's often very easy. It's much easier to extract hypothesized rules of behavior that say, oh, in this certain situation, I know this character or this person or this group would take this certain action. Okay, and again, this may be observable behaviors that we observed in the real world, or it may be desirable behaviors we want in a story or some other interaction. And the question now is, can we infer the numbers from these sort of desired behaviors? Okay, now if we look at we drew inspiration from probabilistic networks, and the idea there was that you can express the output of a Bayesian network as a linear combination of all of the input factors to the model. And then if you say that, oh, this response to my query is incorrect, it should be B instead of A, then you can use the linearity to invert back and infer and what a change to the parameter settings would be to get that desired outcome. And so what we're thinking, like, well, is there a way to translate that idea into a behavior model like an MDP? And so you can imagine that, okay, well, we've got these different aspects of an MDP. We've got a state space, we've got actions, we've got a transition probability, and a reward function. And if we want to make that a linear representation, well, one way of doing that is to say, well, the state is just a vector, and the transition probability, a vector of probabilities, basically, is saying the probability that we're in any particular state. We can have a transition probability that's a matrix that says if we're in a certain state, what's the probability we end up in a resulting state. And then we can have a reward that's a set of linear weights over the state space that we just multiply by the vector that represents the state, and that's our expected reward. And if we could represent the decision-making of an agent as in this way, then that would be great. We could create a linear model of expected value and do an inversion and go back and forth from model to generate behavior, and then from desired behavior to inferring the model. It doesn't quite work that way. MDPs are not quite linear. especially in general and specifically within modeling people's behavior. So as you can imagine, there are many different ways you can imagine there being nonlinearities. So reward may not be linear. It may not be always increasing with a certain state feature. It may be that we just want to achieve a certain goal. So reward may not be linear with our position along a path. It may just be, if I get into the end zone, I score. If I don't, it doesn't really matter. Probability is not linear. It's often conditional on the state. So if I'm in a certain state, there's a certain probabilities. There's certain transitions that may be possible that aren't possible in other states. Well, that's a subtle point. But more problematically, choosing the best action is a maximization. You're looking at all the expected values of your possible actions, and then you're choosing one of them. So you're doing a maximization, and that introduces a definite nonlinearity into the overall function. But what you can do instead is say, well, okay, we can't get pure linearity, that's fine, but can we at least get piecewise linearity? Okay, and so here the idea is that, well, if we can at least have linearity in some parts of the space, then at least in those spaces we can potentially go backwards. And we can do something like, well, let's use a decision tree where we have linear branches and linear leaves, and we can combine them all into a value function. And then that's a piecewise linear function of the modeling parameters, and go backwards again. And then we say, like, okay, I've got a value function that's piecewise linear, and it's saying that the value for the action I want is lower than the value of the action I don't want. Okay, and now can I go backwards and say, what's the constraint on the reward function? And I don't have time to go into the math behind it, but the idea here is that basically you have, for example, a weight of the value of hurting the victim and a weight for peer approval in the reward function. And every time you observe a behavior, it basically rules out some space of those weights because it imposes a linear constraint on what the parameters can be. And so as you get more and more observations, you're basically saying that there is a smaller and smaller space of possible weights of the goals that are consistent with those observations. And as long as you pick a value in this space here, you're going to be consistent with those observations, and you're hoping here that you're generalizing in a nice way and that you're sort of gradually, if you get enough observations, you'll eventually converge to some sort of, to some correct value, but that's an open question. But again, the idea here is that we're trying to take an underlying model of an underlying parameter space where a person modeling a class may not be able to just go in and say, oh, I know what the relative weight for this bully is of hurting the victim versus peer approval. That's unlikely to happen. But you can say, have a teacher perhaps describe the bully in terms of under what conditions would he pick on the victim or not, and use those as constraints on what the overall weights can be. And what's nice about this inversion is that what it's really doing is finding sort of sensitive transition points between behaviors. So if you look at what this constraint is, these lines are where the two actions are actually equivalent. And what we can do is say things like, well, not just use it to fit the parameters to make because it's not just the authoring that's hard. Okay, let's take a step back for a second. You create the agents, and let's say you manage to do, you understood the interface enough and you understand MDPs enough to be able to create an agent model. Okay, now the agent actually takes a behavior, and it's not the right behavior you want. You want to understand why did that agent do that behavior. And it could dump out its computation of the value function. It could dump out everything it did in all of the value iteration or whatever. That's not going to help a user. And so the question is, can we actually find the most salient features that were relevant to that behavior choice? And we can use this sort of same constraint generation mechanism to sort of do a sensitivity analysis to say, where are the points at which that behavior would change from the current behavior to other behaviors? And perhaps that would identify the sort of weights that are relevant to most salient to that particular choice of behavior. And what's also interesting is it actually suggests variations of possible interest where you can say, well, okay, you chose this action. This is particularly relevant for things like health interventions. You know, if you take an action, you say, okay, here's a message I'm going to give to get people to stop smoking. And yes, I think it'll probably work given the current model you have. However, it's very sensitive to error in one of your dimensions of your model. And if that estimated parameter is off by 1%, then the model will give you something different. So the idea here is not just to give a model that gives you a single prediction, but try to actually understand the dynamics and contingent outputs of those models. Yeah. So just kind of to start wrapping up. So this has actually been used in a variety of training simulations. That's the most recent aspects of it. Basically to try to generate the behavior for agents in different scenarios where we're trying to teach a student some type of social skill. So for example, bilateral negotiation, that's the top screen here, where you have a face-to-face meeting with a certain character who's trying to, you need some concessions out of this character to get some advance your overall mission. And you have multiple characters you're going to be meeting with. And these characters all have different personalities, different things they want out of you and are willing to give you. And the idea here is that by having an author quickly encode, okay, these are the things this character wants, and this is what kind of negotiator this person is, whether he's sort of a hardball negotiator or he's looking for more of a win-win outcome. And so by tuning those kind of knobs, the author can generate a completely different character and generate a set of different characters with different negotiating styles that the student can negotiate against and get a better sense of what kind of things they should, how they should behave in a negotiation. And basically teach them that there is a variety of personalities that you're going to meet in a negotiation. The bottom screen here is from the Tactical Language Trainer. We're just trying to teach language and culture by, again, having different characters here. And they're also illustrated. You probably can't see that in this resolution, but there are two different characters that the trainee is basically just going through and talking to different people and trying to achieve a certain mission, but just by gathering information, really. And the idea here is that they're trying to speak in the language, the foreign language, and use the culturally specific gestures that have been encoded into the agents. And the agents are observing and responding to the agent, to the student in such a way where they're, again, using things like the automated liking mechanism, where they can see what the agent is doing, what the student is doing, and interpret it through their own perspective, and then change their thoughts about whether they actually trust and like the student enough to help him in his mission. Okay. So just to summarize here, I've gone rather quickly through the sort of the general architecture with some reasonable recursive planning algorithms. We've been heartened to see how many different social phenomena have been able to capture using this underlying decision-theoretic language, which it's cast as it's a prescriptive language for just saying what is the optimal action to take in situations. But you can actually take that basic fundamental computational building block and reuse it to capture what is seemingly irrational behavior in humans. But what's interesting is that it's not really, it's irrational, but it's also informed by expected value calculations. And that's, I think, kind of an interesting take-home message, that people are irrational within a very narrow scope, but if you actually look at what is guiding their decisions, it tends to always be some form of value. And what's also interesting, one of the key reasons I think looking at human social reasoning is important is that when we look at multi-agent reasoning, multi-robot reasoning, it's a provably intractable problem to do optimally. But clearly, when we look at how people interact in social situations, they are very effective without too much cognitive burden. I mean, we may not be optimal, but we do manage a lot better in our coordination than most agents and robots do. And so one of the key things one of the key outcomes we like is that if we can find the shortcuts that people use in doing these computational models of social reasoning, perhaps they give us insights into how AI entities can also do that same kind of social reasoning. And I'll stop there. All right, thanks. Sure.
First is, so you have some demo applications for PsychSim up there.
Mm-hmm.
I'm kind of curious, and you have a lot of theoretical grounding for it, and I'm curious if you have any empirical discussion of accuracy for it. It always seems like a problem for any system. And the second question is, you didn't really talk about it, I don't think. The last of the applications was for thespian, for interactive drama.
Mm-hmm.
And I'm curious, do you use the model in its standard state for that, or do you tweak it specifically for particular, for drama?
Okay. I'll try to remember the second question as I answer the first one. So empirically, yes. So we've tried to capture data, and one of the challenges here is that what we're developing, so the individual applications are deployed and tested in total. So you have something that's going to teach negotiation, you put it into a classroom and see whether it teaches negotiation. Now, it succeeds at that, but does that mean that the underlying simulation is somehow correct? Not necessarily. And so what we're trying to do in the next step is, okay, we've got an overall application that uses the agents to teach to train negotiation, to train these things, but can we actually evaluate the simulation in isolation? And that's a pretty hard problem, mainly because, if there is an error, if somehow the agents do something wrong, is that PsychSim's fault or is it the model's fault? There's a credit assignment problem there. And so it's hard to gauge the correctness of the behavior. What we have are qualitative assessments where people, experts play the game and say, we didn't see any incorrect behaviors. But again, we're operating in a space where, yeah, I mean, we love talking about possible ways to address this. So that's a huge problem. We're basically just trying to throw it in front of people, gather data with people interacting with it, and hoping that somehow we can get some insight by looking at the data and say, oh, here's something that's wrong. Hopefully we want to see something that's wrong first, and then that would suggest something that we can perhaps measure in the future, but we don't have a solution for that yet. Regarding Thespian, PsychSim is doing the reasoning. It's basically an abstraction layer to assist authors that are with more drama-specific things, like different turn-taking mechanisms. Like if you want to be able to express who's acting when, there are things like social norms that have been encoded in. I mean, we don't really make too much talk about the distinction because it's kind of a blurry line. If you want something for interactive drama, you can use either one. They kind of borrow components from each other. So that's. Yeah.
So when you build a model, have you thought about the underlying social network between the people? So how the student is related to another student and how the teacher
Yeah. So you can create social networks. Basically, there are things like liking and trust relationships. There can also be student-student relationships. There are two different issues there. One is, in some cases, we can build a sort of domain-independent dynamics for them. So how is a relationship going to evolve? So if there's a political relationship between two entities and they take certain actions, then we have a model of how that might affect their future relationships. And there's certainly cascading effects. So one of the things, I can't remember which domain has this, but if you take an action that helps somebody, then they're going to like you more. And also, people who like that person you helped are also going to like you more, but to a lesser degree. And people who don't like that person you helped are going to like you less. And so you can do things like have that social network and then have so the action that you do to take effect, one node in that network can percolate as well and cascade across that network as well. But I don't know, that's still, I think, we have sort of trial ways of doing it, but I don't think we have a good general solution for that.
Have you thought about applying your bullying simulations to combat the new threat of cyberbullying?
So the bullying thing is kind of an interesting example in that we've never actually gotten funding to do it. We just kind of play with it, mainly because it's a more benign example than a lot of the military simulations. So we've tried to get, we have social psychologists on campus that we talk to about bullying and try to build this model, but we've never actually been able to pursue it, more, in terms of, so when we first did this was, again, cyberbullying was not the issue. So I'm sure if we talked about this now, the psychologists would have much different ideas about what the relevant features are. But no, I think it'd be really interesting to do. Of course, then it's a harder network too. Yeah, Thomas.
So I want to come back to this recursive MDP. So
Mm-hmm.
it seems that you're using the learning from the training examples, assuming that those models are correct, and then inferring the state. But it seems that it's very sensitive then to those models being correct.
Yeah.
I was wondering, how do you manually come up with those models, and how big are they, and so forth?
Right. The fitting is taking one piece of the parameter space and providing automated support for it. But really, the hard work is in building not even a model of the agents, a model of the world. Like, how do you actually build a model of, okay, if I pick on this kid, what happens to him? If I punish the kid, what happens to him? And if there's an urban, the example I put up was, there, the agents have like 30 different actions affecting 20 different state features. Social scientists, God bless them, put in the models for all those different combinations of effects. But yeah, that's we can provide some fitting support at the end to tweak, 8 parameters in the reward function. But I think we have ideas about possibly doing that from a data-driven point of view. Like, you go through news stories that are relevant to your scenarios and try to extract some sort of model that says, here are the relevant features and here are the effects of certain actions. But yeah, no, that is still the huge authoring burden, is in building a model of the world. It's not solved by any stretch of the imagination. Yeah.
So how computationally intensive are these? I mean, to solve this, and entities are not the best quantities, but
Right.
still, you seem to have lots and lots of features.
Yeah, well, what's interesting about the scenarios is that we only need to simulate them to the degree that is needed for the scenario. So like, so in the bilateral negotiation scenario, it's a one-on-one interaction, so there's only one agent at a time. But on the other hand, it's got 30 different things it can offer or request, and it's looking enough steps into the future to see past the end of the negotiation. And so for there, we use an abstraction over the state space, and do a value iteration there, and we compile a policy that it execute in real time. In the urban scenario, which is that's the screenshots I showed, there are 100 different entities, 30 different state features, but they're not very smart. They're looking very shallowly into the future. And so what ends up happening is that we've either had the complexity is in the number of agents that aren't very smart, or you have one very deep interaction with 1 or 2 agents. And so the complexity is sort of comes in different ways. And so we have, you can do different abstractions. What happens when we have a 100 entities simulation with 100 smart entities? Yeah, that's still an open question. But in a lot of social scenarios, you don't need that kind of richness because, beyond a certain point, additional complexity is just noise to the user. You can make them smarter, but the person's not going to notice, so why bother?
You talked about communication there. I thought was a neat thing for a second. Within the decision-theoretic framework, you can set up, okay, this is a state, that's something I can communicate.
Right.
But how do you choose what to actually communicate? Because you have a whole bunch of stuff. You don't say,
Yeah.
I'm still alive.
Right. So communication was actually the initial reason we did this project, and really what we model communication as, it's an intended change of beliefs for the person hearing your communication. So when you're saying a message like, I am stronger than you, what you want is that person that's hearing that message to believe that, and somehow that's going to change their behavior. So there's no point in saying I'm alive if you think they already think you're alive, or if telling I'm alive isn't really going to change them in any way. So what we model is, if you send a message, you model, okay, if they change their beliefs, then how is that going to change their behavior, and how is that going to impact my reward? So the idea is, it's still based on the expected value, but you still have to sort of circumscribe the space where they're not considering a whole bunch of options.
So it's a very computationally expensive search.
Right. Well, so what you can do is, but you can prune a lot of those ahead of time, because some of those messages are never going to impact your utility, so you should never even consider them. And so what you want to do is look at the messages. You can look at, sort of do an offline process, and that's another thing that comes up here, is a lot of mixture of offline and online reasoning. And if there are things you can do offline, like prune messages that are never going to have any meaningful value to you, then that can save you in the online computation. Yeah.
Okay, we have any more questions? No? Then let's thank the speaker.
All right. Thank you.